Okay. Our next talk will be from Andreas Krenmeier from Austria. He will talk about secure server daemon programming under Unix and will show us some pitfalls which are not so obvious, but you should, of course, handle in your code. And he's working for a software development company in Austria. Have fun.
Hello everybody, welcome to my talk. I'm going to talk about the topic secure network server programming on Unix. It's about the dangers and pitfalls of implementing a server daemon that provides some sort of service. And I will talk about how to avoid the biggest security issues. A few bits about me. I'm Andreas Krenmeier. I work as a software developer. I have, an interest in security-related topics. It doesn't mean that I'm really the superhero or whatever in this area, but, I did some work and it's quite interesting for me. Some of my previous works are the prototype for a new type of network intrusion detection system that I presented about 3.5 years ago at the camp at this time, and Contra Police. That's a heap smash prevention facility. It has been mentioned last year in the talk about memory allocator security. So some of you maybe already know about it. And here I'm going to present something new. I'm going to talk about Trapdoor 2. I will talk what it exactly is. I will talk about it later. And it's an example for, how to securely program. So the agenda is a general introduction. Then I will talk about the design and implementation of Trapdoor 2. Then about the possible attack vectors, the obvious ones, the not so obvious ones. So implementation errors in Trapdoor 2 itself, implementation errors in SSL, TSL implementations, and what we can do about denial of service attacks right at the application, and some of the conclusions then that we can draw from it. So as an introduction, a very simplifying view on writing secure code. Write secure code as summary. Don't use system and be careful with buffers. And then an answer on /dot. Brain surgery summary. Open skull and poke around with stick. So a more sophisticated view on security issues than this is definitely required. And this summary doesn't even scratch the surface. General coding style. There are really a lot of papers and articles about secure programming with language like C or C++ or whatever. But this is beyond the presentation. This presentation really doesn't cover any language-specific security issues. Everything I'm talking about is more on the operating system level. So even you use a more secure language than C, this can be still interesting. So I will talk about issues that, cannot be prevented by the language itself. So my advice is anyway, use more secure languages like Dylan or C++, if you have the freedom to do so. And that's a practical problem. There are so many great languages out there where you can really securely program, at least on the level of buffer overflows, so that kind of stuff is prevented. But when you're working in the industry, you hardly have any chance to use these languages because there is so much legacy code that you cannot simply rewrite because there's so many man hours, man months, man years in it. You cannot simply throw it away. After all, it's most of the legacy code is more or less well tested or widely used. So there is no chance practically to use Dylan or Eiffel or other kind of other languages of that kind, simply because you have to build upon something and cannot start from scratch. And I mentioned C++ as a more secure language. Be sure to use modern C++, and by modern C++ I mean all the features and stuff that comes with the C++ standard library. In my experience, most people who learn C++ do not learn about this really interesting standard library. You can do really a lot of stuff with it, and you don't need to do any basic zero-terminated string handling or anything like that. And you produce cleaner code, better code, and definitely code with less buffer overflows. Nevertheless, chapter 2 is written with C, and we had a hard time getting it really secure. Well, it's not 100% secure, so if you download the source code from the website, I'm pretty sure the one person or the other will find some bug. So nobody's perfect, just as a disclaimer. Yeah, about chapter 2 itself, where does this come from? My co-developer Clifford Wolf, some of you probably know him. He regularly does lectures at the Chaos Communication Congress, and he worked on Rock Linux, and he had the necessity to poke holes into firewalls. That means to allow a certain computer to connect to, for example, SSH, but only for a time window of 30 seconds or something like that. And the first solution was called Trapdoor. It was telnet based. You simply connected using telnet, entered a secret code, and then the SSH port for your source address opened, and you were able to connect. Of course, telnet, insecure. It was clear that it had to be reworked, and the improvement is Trapdoor 2. It uses HTTP instead of an ad hoc telnet-based protocol, and more security through the use of SSL. So we only allow HTTPS use. So it's not possible to sniff those magic codes or magic cookies, as we call them. So. The basic principle is you're entering a magic cookie, and that magic cookie is associated with a certain command. For example, opening the port for the source address for a certain amount of time, or doing whatever. In my old company, we used it to restart certain services that were quite flaky. We could even use it from the mobile phone via WAP, and so it's quite flexible. But the main idea was this trapdoor thing. Anyway, you're entering the magic cookie. The HTTP request is received. The magic cookie is checked, and if it's okay, the associated command is executed, and then the success status is sent back to the client. So the naive and really simple approach we took was a master process that accepts the connection, it forks. Then you have a child process which again forks and is connected via a socket pair. No, actually I used 2 pipes, but it would be the same if you use a socket pair. And this child process drops the privileges, receives the HTTP request, hands the cookie to the parent via the pipe, the parent, this child process, then checks the cookie, runs the command if the cookie was okay, and sends the status back back to the process. And the unprivileged child then sends it back to the client. That's quite simple. We use this two-stage thing because you obviously cannot interact with the client, which is the potential attacker, with a root process. And you need root permissions to run this command here. So it's really the naive approach. And of course, this famous quote, for every complex problem, there is a solution that is simple, neat, and wrong. Chapter 2 is not really wrong, but when we looked at it closer, after we wrote the first version, we found some obvious and not so obvious flaws. And so we looked a bit further and then implemented code to prevent certain attacks. And the main attack vectors we identified was, first of all, implementation errors in chapter 2 itself. For example, buffer overflows, integer overflows, all that kind of usual stuff you have to care about when you use a low-level language like C. Then another main attack vector is the SSL implementation, like for example OpenSSL or GNU-TLS or whatever you use. And there are also denial of service attacks, which can become a huge problem since we fork 2 times and new processes usually take quite a few of resources, memory, CPU time. So you need to prevent your own resource starvation. But what we cannot really care about is that are logical errors. But ideally, such logical errors should be found through unit tests. We haven't implemented any unit tests, so as I said before, we're not perfect. But C code, unless you really design it from the very beginning to be capable to be unit tested, it's almost impossible to write really good unit tests. Usually C code is very coupled. At least I haven't seen any really good C code that was unit testable, at least not in the industry. Yeah, let's talk about the implementation errors themselves. As I mentioned before, yeah, chapter 2 runs with root privileges, which is a big threat. And so you have this one child process that interacts with the client, and you really have to apply the principle of least privileges to this child process. That means you need to drop the user, the user and group privileges. You need to put the process in a change root environment so that there is no possibility to interact with the environment of other processes with possibly higher higher privileges, and that this unprivileged process has no access to a usable file system. And of course, the communication between the two child processes, the unprivileged child process and the privileged child process, is going over 2 pipes, or you can also use a socket pair. And we use a strictly enforced communication protocol. And of course, what's also very important, you have to enable really strict resource limits. A few code snippets. Yeah, that's not really interesting. drop your group and user IDs. Be sure to drop the group before the user ID, because otherwise you may not have the permissions anymore. Then what's also very important about change root doesn't really work unless you change your current working directory to the change root directory. You always need to care about this. So either you do it this way or you do the change root first and then a change directory /. And as you can see here, always check about return values. Actually, this code is quite boring, but that's the simplest way to show this all. The communication between the two child processors, well, as I said before, it's quite boring code. But what we always checked was that certain sizes were not overrun, so that no buffer flow of any kind can happen, and that's really crucial, because that's really one of the attackable parts. So you need to get that right. So design your communication protocol as simple as possible. A few more words on resource limits. What we did was we limited the maximum CPU time that the child process may use to 2 seconds. We found it to be enough. We limited the maximum size of the data segment, the maximum size of the stack, the maximum size of the RSS, and the maximum real time. And that is really important, because that makes it really hard to take over the unprivileged process, which is in its change root environment, and use it for any long-running tasks. Even if it's unprivileged, and you can take it over and use it for a long time. You can use it for zombies, for botnets, because even then it's in the regular conditions allowed to bind to a high port and accept network connections. And that's why you need to enforce that, so that after 10 seconds the line is cut and the process dies. So that's how you can well, prevent that your unprivileged child process is used for any, for example, sit at home, or as a zombie for a botnet, or any other distributed computing effort. Again here, the set R limit. It provides quite a few options what you can do. And the best advice for the values that that we use is that you should use is just experiment. It's really difficult to find it out, and experimentally we found out that the values we used worked good enough. We had some issues with GNU-TLS, because we support both OpenSSL and GNU-TLS as SSL library, and GNU-TLS requires a lot more resources. So it has a minimum requirement of something like 32 file descriptors, and we needed, I think, 8 seconds of CPU time, because it does some really weird stuff like busy waiting. So it really takes up a lot of CPU time. And this whole principle with putting an unprivileged process into a change root environment and having it communicate with a privileged process is called privilege separation. Well, you're using the unprivileged process is, of course, unprivileged. It means it has a user ID and group ID of greater than 0. It's in a change root environment. Resource limits are enforced. It directly communicates with the client, and the client is the attacker or potential attacker. And it also communicates with the privileged process. But the privileged process only does the few things that really need higher privileges than the completely unprivileged process. So usually these aren't a lot of operations. In our case, it was only the checking of the magic cookie and running the command, calling the IP tables binary. Yeah, as mentioned before, this concept is called privilege separation. It was first described in a really good paper with the title Preventing Privilege Escalation by Niels Provos, Markus Friedl, and Peter Honeyman. And the first implementation was OpenSSH. And OpenBSD, in its effort to improve overall security, implemented this concept of privilege separation in virtually all servers they provide, like NTPD and syslog daemon. And it seems to work, and it's quite cheap to get a lot better security. So it doesn't take a lot more resources compared to other means of defeating attempts of attack. Yeah. Another important thing are implementation errors in SSL and TLS. This is something that people usually do not really care about, because it's a piece of software, black box, just a library that you use, and that's supposed to work. But SSL, TLS implementations have been shown to be vulnerable in the past, and that's why an attack against the SSL implementation is really likely. I found a few numbers, and the Secunia, this, I think, Swedish security company, they have 11 OpenSSL advisories from a time span from 2003 to 2006, so that's quite a lot. And the US CERT, Department of Homeland Security, has 21 OpenSSL related and 4 GNU TLS related vulnerabilities in the last 3 years. So SSL is really something that is quite likely to be attacked, so you need to care about it. And so we looked at how you usually implement SSL and found quite a simple solution, because usually you first read keys and certificates from the file system. You initialize the SSL subsystem. It does, let me see, it loads error strings, you add algorithms and other fancy stuff. Then we enter the change root environment and drop all privileges, and then we initialize the actual SSL connection. And that's the point where the attacker is first able to interact with us at all. So the first contact, the first interaction is already in a secure environment. And as mentioned before, Trapdoor 2 supports both OpenSSL and GNU TLS in order to provide an alternative in case one of the two has been compromised. So I told you the numbers before, it's quite likely, and when you see shit, an unpatched OpenSSL vulnerability, let's switch to GNU TLS. Although the code quality of GNU TLS in some parts is quite dubious, so I wouldn't really recommend it. But after all, there aren't that many SSL implementations out there, especially not for Unix-like systems. So OpenSSL is really standard. Yeah, just short code snippet. We have this init SSL, which does all the fancy stuff, as mentioned before, load error strings, add SSL algorithms, create the SSL context, loads the certificate, private key, and all that stuff. And the init SSL2, which happens after dropping the privileges, associates the file descriptor with the SSS handler that you need to communicate via SSL. And then it accepts the SSL connection. The third problem we came upon was denial of service. We identified two main points, namely denial of service attacks against system logging, when in the very unlikely case that you do take over process, that you run an attack against system logging or run an attack against forking, basically connecting a really lot of times during a very short period of time. Because too many connections per time frame lead to too many processes and too much system load, and your system may become unusable for users that actually should use it. So in the case an attacker really is able to take over an unprivileged child process, the hard disk could be filled up by when you're running thousands of syslog calls per second. And to slow down such an attack, the number of syslog messages per time frame is simply limited. It's quite simple, and it has the disadvantage that we implemented only a wrapper around the syslog system call called limit syslog, and when some exploit code runs the syslog system call directly, that doesn't quite work. So the syslog daemon actually has to care about this too, but it's not such a great threat anyway. It's only for the situation when, for example, exploit code calls parts of our own code, which very often does syslog calls, and so that's where the limit syslog comes into effect. And the more interesting stuff, credits for this go to Clifford only, because he's the one who developed it, and it's quite simple and quite effective. Yeah, the basic problem is that when you have too many connections per time frame, it leads to too many child processes. In the drawing before, one connection leads to two child processes, so that's quite a lot of resources. And of course, too much system load, your system may become unusable. So you need to limit the incoming connections per source IP. Plus the number of incoming connections at all. But Trapdoor 2 should still be functional and responsive for users from other IP addresses. And that's how we implemented our countermeasure. We use the source IP from the client plus a random value, which changes every 8 seconds. We hash this and divide this by the number of slots and take the remaining part, and this is the slot number, and for every slot the number of connections is counted per time frame. If the count is higher than a certain threshold, then the request is simply rejected before even the fork is going to happen. And after every time frame, these 8 seconds, the counter is reset and the random value changes. The number of slots is currently 397. So that means that only maximum of 4,000 764 requests per 8-second time frame is allowed, but only if the attacker is able to find source addresses so that the distribution for the slot numbers is quite uniform. Clifford developed an own hash algorithm which is quite compact, provides pretty good distribution even for the changing random values. You can also use MD5 or SHA1. All you need is, well, something to get a value from 0 to 396 to get one of your slots. The hashing algorithm is quite simple. That's the code. It's running really fast and it's good enough for what we need. And why do we know that it's good enough? Because we did a few simulations, and on this scale you can see the slots, and on this scale you can see the number of occurrences for a certain slot. And I simply generated 2,000 random IPs and hashed them with the same random value and computed the slot number, and that's how it distributes. Looks pretty good. We didn't do any more formal research. We simply generated the graphics and looked at them, and at least for the random IPs, that's what you usually have when you're having a distributed denial of service attack. You have more or less random IPs. That's one way of distributed denial of service attacks. The other one is when an attacker has a whole subnet and uses it to attack your server. And we also did that for a /20 subnet. And the distribution looks different. And that's just one example. And it's really weird graphics, but we couldn't find any modifications to the hashing algorithm to significantly improve that. But it's good enough anyway. I generated a few more because, as I mentioned before, every 8 seconds this random value changes. So every 8 seconds you have different kind of curve here. So at another time frame it may look like this. 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 Or this. So it's not really easy to predict how the distribution really is going on. As you can see, the second graph, or the number of graphs that I showed you from the /20 attack, it isn't uniformly distributed, but it exposes an interesting paradox. Since it doesn't provide a uniform distribution, it actually allows fewer parallel connections, because the threshold is, for example, where do we have a good graphic? The threshold is at 12, and so that's quite a lot of connections that are really rejected, and it's really hard to find out for the attacker where this kind of hole is where he can concentrate on with more connections. And so the conclusion is that when you assume that there are no legitimate users in a compromised subnet, this observed property actually reduces the effectiveness of the denial of service attack. So when we look at, looks pretty weird. When we look at the naive approach that we took and apply the changes or improvements that are mentioned here, we did a few things. For example, we have the connection limiting here for the forking. We have here a strict communication protocol for the two child processes that communicate. This unprivileged child process really has as little privileges as possible, and this whole concept with the communication protocol and as little privileges as possible, this all together is the privilege separation. So that the conclusions that we can draw from our work is there are some flaws that not quite obvious, and you need to care about them. And here we described some countermeasures for certain attacks. Just looking for buffer overflows is not enough. And you really need to care about privileges. And it's also always about employing safety nets. So you always need to care about defense in depth. You should not only care about privileges, but you can also tackle, for example, the buffer overflow problem by either using a more secure language or these stack or heap overflow stuff that is implemented in current C libraries or the compilers themselves. Or you can be even more strict on the operating system permission level. At least that things that Unix really allows. Okay, one important thing that I want to mention: nobody's perfect, so shit can happen and shit really happens, and Murphy is omnipresent. So, are there any? Now, first I want to thank a few people. For example, Clifford Wolf, who had the initial idea, the co-author. He's the co-author of Chapter 2. He provided some very valuable things, and a few of my friends who gave me lots of valuable feedback about this whole thing. Here are a few addresses. Here you can find Chapter 2. It's actually we have an old version online where there are quite a few smaller issues still inside. So better check out the current version from the Subversion repository. And also, if you want to know more about it and more in detail, read the paper that's linked in the Fahrplan in the Congress schedule. Also read the source. So we believe it's pretty good. So yeah, thanks for attending my presentations, and please ask questions if there are any.
Hi. You have a bunch of code which is in front of your network and does essentially some authentication via a magic cookie and executes some arbitrary commands. Mm-hmm. Why did you reinvent OpenSSH?
Because sometimes you do not have, for example, when you're at a customer, you never have these perfect conditions where you're allowed to do everything, but you, for example, have only the permissions to use HTTP or HTTPS, because that's the only thing that the client allows, or some other stuff you need to care about. So that's why we implemented it based on HTTP, HTTPS, because it's such a standard protocol and virtually every firewall lets it go through. It's as simple as that.
I'm just curious, with the slot distribution, you said you used your own hashing algorithm. Was there a special reason you didn't use MD5 or SHA-1, or why did you use your own algorithm?
I know using your own cryptographic hashing stuff is bad because that's only the stupid people do. We know that, and Clifford, who designed that, put quite a lot of effort into it, that it's good enough. So we simply used it because it was simple and it worked well enough, and that's all. It wouldn't be much of work to actually use MD5 or any similar algorithm and widely tested algorithm. So it's no problem, and practically from our experiences it wouldn't make that much difference.
Okay, so there was no special reason why you used your own?
No. It isn't any cryptographic hashing magic or something like that. It's really simple code and it works. That's it.
Hello. You change hashing random seed every 8 seconds, yes? To distribute processes in the slots. And the child process limit is, if I remember correctly, 10 seconds. Are these times connected, or let's use 10 seconds because it works? Or
you need this 8 seconds or 10. No, it's not connected. To be honest, I haven't really thought about kind of synchronizing it, but well, it wouldn't be that important because within this 8-second window, connections can happen at any time. So when the process ends, it can be in the next
in different slots.
Next window, time window.
Can you show your slide again with your source code where you read from the pipe? Because I think there's a little bug in there.
Okay.
You have a signed integer for the size, and yeah, go to the slide, please. Yeah, that's
Here.
Genau. You read a signed integer 4 bytes, and then you check if the size is greater than 100. But if the size is now -1, this check will pass, and then you do a cast to size t, which is actually unsigned integer. So -1 will be something like 4 million or whatever, and the read call will, classical buffer overflow, I would say. Probably bad design.
From the quick look, you're right. Shit happens there. Yeah.
So
we will fix it.
Okay.
I want to come back to the connection limiting. This is unnecessary to implement it in the application because at least in Linux you have an IP tables module for that, and it's much better layer for that because you can limit it per network, per interface, and don't have to put all that stuff in your application.
When was this implemented?
I don't remember. I just read it recently.
Okay. Because we started with this in 2003, so
so now you can rip it out.
We could, but there are other Unix systems.
And reduce the complexity.
No, I'd say as a wild guess, there are other Unix systems that don't provide that advanced possibilities as IP tables does. So.
Because I had the problem with IMAP daemons, and they had global connection limiting. It was nice and good, but I need to limit outside connections differently to inner connections, because the inner connections are a lot of people working in the company, and the outer connections are some outsiders connecting, sometimes around 5 or 10 people. They don't need so many connections. So I would limit it differently, but the application doesn't allow that. So I had to resort to the IP tables level anyway. And could not basically use that feature, which is just useless for me.
Okay. Any further questions? Okay, since there are no more people in the queue, I again say thank you for coming and have a nice time at the Congress. Bye-bye.